All right, this is section 11.9, video number 2. So in video number 1, we were talking about how to write power functions as infinite series um, based upon a defining rule of a geometric series a over 1 minus r. We can manipulate series so that we can actually manipulate functions, excuse me, so that we can write them as power series. Well, now we're actually going to introduce, we're still going to be doing power series, but we're going to be able to do it by taking derivatives or maybe antiderivatives and things like that. Because basically, if you want to let your power series, because it is a function of x, be f of x, then we should be able to take a derivative of that. So our first example is relatively basic. The main thing you want to remember here, because I know this can get confusing, is that the function is defined as a function of x. N is not what you're taking the derivative of. So you're not taking the derivative of the n part. It's just the function of x. Basically, the n stuff is you have to treat those like numbers. They're just like constants. So in the first one, f prime of x is going to equal the derivative of that sum. Well, the sum itself doesn't change. 2 to the n is a constant. That doesn't change. But the x minus 1 to the n power, that is the function of x. So because remember, the ultimate idea here is you're creating polynomials out of these things, so it's going to follow a basic power rule. You'll bring the power out to the front, which is n. You'll reduce the power by 1. And then you're going to technically multiply by the derivative of the inside if there happens to be something attached to your x. But that's it. That is the derivative of that power series. So you literally just bring the n to the front, reduce the power by 1. Okay, let's try another one. So our derivative of our power series, n equals 0 to infinity. So let's see, we're going to bring the 2n, because remember, the n factorial is just a constant, so don't freak out and be like, how do I take a derivative of factorial? You don't really. There is a way to do it, but we're not messing with any of that. But the n has nothing to do with it anyway. So you're going to bring the 2n to the front, reduce the power by 1, and then the n factorial in the denominator just stays there. So there you go. That is your derivative. Now, I should mention that when we took the derivative and we reduced the power, we really need to increase our n values. So let me go ahead and erase this. I forgot to do that. Because if you were to leave n equals 0, which is the way I had it in first place on both of these, and you plug a 0 into here, you're now going to get something where it's x minus 1 to the negative 1 power. Well, that's the same as 1 over x minus 1. That is no longer a polynomial because you can't have the x's in the denominator like that. So we really have to increase the starting point by 1. Otherwise, it's technically not a polynomial anymore. So you just have to be careful on that, and you have to do the same thing on this one, because if I left that as 0, we would have had x to the negative 1, which would have not been a polynomial. All right, it actually wouldn't have mattered too much because each one of them would have been multiplied by 0, but you just got to be careful. All right, the derivatives are not that difficult to do overall, though. Again, you treat them as a polynomial. Bring the power out front, reduce the power by 1. Antiderivatives, same idea. We're just going to take an antiderivative. There's obviously just one extra step here, so we're going to take the antiderivative of f of x. We'll call it capital F of x. That's our antiderivative. So let's see, we'll write the sum n equals 0 to infinity. Negative 1 to the n is not an x part, but this part is. So we're just going to raise the power by 1. So it'll be x minus 1 to the 2n plus 2. And then like with other antiderivatives, we divide by the new power, which is now over 2n plus 2. And you might be thinking, why did he leave that little space there? And hopefully that's what you were thinking. Well, the general concept there is, remember with an antiderivative, because this is a family of functions, we have to include plus c. The difference is we don't typically put the plus c at the end because unless you want to write the entire thing in a big old parentheses or bracket, which is fine to do, if you put plus c out here, it looks like that's part of the sum, which it actually is not. It's out in front of the sum, or it's a separate part from the sum. So you have to remember your plus c. Typically, it's going to go in the front now, just to make sure. Okay, one more example of an antiderivative or an integral. If we wanted to integrate f of x dx, we would take the antiderivative of the lowercase f of x. So our capital F of x here is going to be the sum n equals 1 to infinity. I did not leave myself enough room for that plus c. There we go. So that's going to be, let's see, x minus 3 will raise the power by 1. That is now n plus 1. And that's going to be now divided by n plus 1. Don't forget we still had an n factorial down there to keep in the denominator. And we have to write our plus c. And there's nothing wrong with what I wrote there. What you might want to think, though, is that this could be written in a different way. So it'll still be c plus n equals 1 to infinity for the sum, x minus 3 to the n plus 1. But n plus 1 times n factorial is really the same thing as n plus 1 factorial. Okay, they mean the same thing. All right, so why am I going through all this? Like, why is this necessary to do? I am so glad you asked. So we want to find a power series for the natural log of 1 minus x. Well, if you look just at the natural log of 1 minus x, obviously, as it stands right now, that is not in the form 1 over 1 minus x. It's not even in a fractional form. So sometimes you have to do a little manipulation to get it there. What I know is that the derivative of a natural log gives me a 1 over in some form. So what I can do is I can say, okay, let's take the derivative of the natural log of 1 minus x and see what that gives us. Well, following our rules, that's going to be 1 over 1 minus x times the derivative of the bottom, which is negative 1. So is this now in the correct form? It sure is. It's got an a over 1 minus r. So a is negative 1. R here is technically just x. It doesn't really change in this case. So we can start writing our power function. Always start with the basic one. 1 over 1 minus x. That is the sum of x to the n as n goes from 0 to infinity. So now we're going to substitute x. Well, we don't have to substitute x in. It's kind of already there. But we are going to multiply the entire thing by negative 1. So now we're going to go negative 1 over 1 minus x. There is nothing that's going to change anything if I multiply the negative 1 either inside or outside of the sum. I don't have another negative 1 on the inside to combine it with. So literally, we can just kind of throw that negative out in the front. Okay, because it's not being raised to an n power, so it does not have to go into the inside. So that is the series for negative 1 over 1 minus x. However, negative 1 over 1 minus x was actually the derivative of the original one that we had here. So in order to get back to the original one, now we have to integrate or take an antiderivative. So the natural log of 1 minus x we know was the antiderivative of negative 1 over 1 minus x. So I need to take the antiderivative of my series. So I'll put the c out front. Technically, it's plus the minus, so I'll just leave the minus. And now the x is going to get raised to the new power n plus 1, and then we'll divide by n plus 1. In order to actually complete this, we're actually going to say, okay, can we figure out what c is? Well, there is a specific value that we can let x be in both sides of this equation that will find a value for C. Usually the easiest one to use here is going to be 0. If I let x equal 2, let's just say x is 2. Over here I'm going to get a 2 to the n plus 1 power over n plus 1. That's not an easy sum to simplify. But if I let x equal 0, now I've got 0 over over n plus 1, which is 0. The sum of 0 is just 0. So basically it's going to go away. So the reason that we're going to pick that is for that specific reason. We are going to pick, erase that real quick, we are going to pick let x equal 0. And if that's the case, now what you get is the natural log of 1 minus 0 equals c minus the sum of 0. The sum of 0, of course, is 0. The natural log on the left-hand side is the natural log of 1, which is also 0, which just means that c here is 0. Will that always be the case and it's going to zero out? No, but it will happen more often than not. So ultimately, in this case, it means that the natural log of 1 minus x can be written as the sum n equals 0 to infinity, x to the n plus 1 over n plus 1. Oops. Minus negative sign out front. Sorry, almost lost that. Okay, a few more. Find a power series representation for the arctangent of x. Once again, arctangent of x is not in that form, but as I've been mentioning for most of the year, you need to know its derivative pretty quickly because it is one of the more common ones we deal with. So I know that if I were to take the derivative of arctangent of x, that's going to be 1 over 1 plus x squared. Okay, that is pretty much in our a over 1 minus r form. We can rewrite that as 1 over 1 minus negative x squared. It'd probably be better to write it that way. So now I know that a is 1 and r is negative x squared. So now we can start building our sum. 1 over 1 minus x is the sum, and goes from 0 to infinity, of x to the n. Again, that's the common one. We'll replace x with negative x squared. So 1 over 1 minus negative x squared. Replace x with x squared in your sum. So you get negative x squared to the n. Again, probably best to go ahead and rewrite that, especially now that we're taking derivatives and antiderivatives. It's going to help. That'll be negative 1 to the n, x to the 2n. So that is 1 over 1 plus x squared. But we don't want 1 over 1 plus x squared. We want the arctangent of x, which is the antiderivative of 1 over 1 plus x squared. So the arctangent of x is going to be the antiderivative of the sum we just found. So we'll put c plus n equals 0 to infinity, negative 1 to the n. So that'll be x to the 2n plus 1 over 2n plus 1. And how can we figure out the c value? Once again, if we let x equal 0, we'll find that c is going to go away. I'm not going to write the whole thing out here, but if x equals 0, c will be 0 because you'll be taking, once again, the sum of 0, and the arctangent of 0 is also 0, so c is going to be 0. What I will tell you is this one right here will come back. So you're going to want to keep this one starred or something like that. This one is going to come back to us. Arctangent of x is that particular sum. All right, just a couple more. How are we doing on time? Doing good. We're at 14.5 minutes. Okay, let's find the power series for the natural log of 1 plus x squared. Same general idea. Let's get it into a form of a over 1 minus r. Take a derivative. So if we take the derivative of the natural log 1 plus x squared, that is going to be 1 over 1 plus x squared times the derivative of the inside, which is 2x. So really what we get out of that is 2x over 1 plus x squared, which means a is 2x and r, again, is negative x squared. Okay, again, I'm hoping that you can see this. So, well, the interesting thing is we don't have to go through everything that we just did. We could. We could go through everything that we just did in the previous problem, but what we found in the previous problem was a representation for 1 over 1 plus x squared. So I'm just going to kind of jump back to that fact, and you can look back at your previous page, but we don't have to start all the way from the beginning because we did get to this point, 1 over 1 plus x squared. That ended up being sum, and goes from 0 to infinity, of negative 1 to the n, x to the 2n. Well, now if all I want to do is introduce the a value, which is 2x, we're going to multiply the top by 2x. So multiplying the left function by 2x means we multiply the right function by 2x. So now I'm going to have a 2x times x to the 2n, which will be 2 times x. See, 2n plus 1 will be your new exponent. Okay, we are down to the point now where all we have to do is, because this is the derivative of natural log of 1 plus x squared, so now to get back, we need to take the antiderivative. So the antiderivative of the left function here is the natural log 1 plus x squared. So the antiderivative of here on the right side, again, negative 1 to the n stays. We will increase the power by 1, so it's now 2n plus 2, and then divide by the new power, 2n plus 2. And I forgot my c. There we go, c plus all that. Once again, plugging a 0 in is going to give you 0 on the left and just c on the right, because the sum of 0 will be 0, so we can get rid of the c value since we can use 0 for that, for the x value. But we can simplify this just a little bit more. It's not necessary to do, but hopefully you can see that there is a 2 on the numerator and 2's in the denominator that will all cancel out. So really what you get is the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 2 over n plus 1. All right, one more to go. Find a power series for 1 over the quantity of 1 plus x squared. Time. Okay, we're still doing good on time. All right, the last one here takes a little bit of extra time. So this one looks like it might be kind of in that general idea for us to be able to use a over 1 minus r. The problem is that squared. If you were to literally square everything in the denominator, you're going to get something which is not in the right form, right? You would FOIL that thing out, or however you want to say it, and you would get a trinomial out of that in the denominator. We can't have that. So this one's going to be a little bit different. You have to be able to recognize this is what's going to happen. We need to integrate this one first, or take the antiderivative first. So you can think of this as 1 over, you can think of it as something like 1 over some, no, I don't want to use a, something to the second power, which is the same thing as, u to the negative 2. Right, and this is going to work because there's no coefficient out in front of the x to make this a problem. The antiderivative of u to the negative 2 would be u to the negative 1. Dividing by negative 1 is the same thing as multiplying by negative 1. So ultimately, the antiderivative here is going to be negative 1 over u. So think of the 1 plus x squared as the u. So the antiderivative, or we can write it as an integral, I guess, 1 over 1 plus x quantity squared dx is going to be the same thing as the antiderivative. So that's going to be negative 1 over 1 plus x. Okay, now we're at least in the correct form. because now your a value is -1 and your r is -x. So start off with 1 over 1 minus x, which is the sum of x to the n. Okay, let's build it. Let's replace x with -x. 1 over 1 minus -x. Replace the x here with -x, so we'll get -x to the n, which again, distributing that n, because it's important to do this while we're working with integrals and antiderivatives and derivatives and all that kind of stuff. So become -1 to the n, x to the n. We do need to multiply through by a -1. So let's see, multiplying the -1 to the n times a -1 will literally just give us a -1 to the n plus 1, and then x to the n power. All right. But remember that this right here, this representation was an antiderivative of the 1 over 1 plus x, that quantity squared. So in order to get back to the 1 over 1 plus x quantity squared in the denominator, we need to now take a derivative. So 1 over 1 plus x squared is now the derivative of what we just had. So let's see, that'll now be n equals 0 to infinity, -1 to the n plus 1. Taking a derivative, we bring the n down and reduce the power by 1. Now remember, we took a derivative, and technically it wouldn't be a problem here because plugging 0 in for the first n there, the n that's being multiplied by the x, would make it 0 out anyway, but we should technically raise that first index from n equals 0 to n equals 1 to get rid of that term. So the finalized answer here should be n equals 1 to infinity, -1 to the n plus 1, and x to the n minus 1. And that's it. That is the power series representation for 1 over the quantity 1 plus x squared. All right, that should be good enough to get us going. Again, remember the idea is that we are building power series representations. We're making polynomials out of things which are currently not polynomials. That's what we're doing.